Okay,
So will I
welcome
start?
everybody. So to our second short talk session by PhD students and postdocs. So this will be the last BPS of the semester. So we'll be having four speakers. So we'll start with Priyanka Sen from ISI Kolkata, who will be speaking about random matrices. Over to you, Priyanka.
Good afternoon, everyone. So as the title of my talk goes, I'll be talking about random matrices with independent entries and beyond non-crossing partitions. This is a joint work with Professor Anugu, Kaushik Saha, and Usharko Sen. So today I'll be talking about spectral distribution, Wigner matrices, semicircle law, and how the non-crossing partitions play an important role. We'll ask some questions, try to answer them, and we'll see something called special symmetric partitions and what we can do about them in future. So here's the outline. Now, let A be a n cross n random matrix. By that I mean that the entries are random variables, and lambda naught to lambda n minus 1 be the eigenvalues of the matrix n. So obviously, since the entries are random, the eigenvalues are random too. Now the empirical spectral distribution ESD is defined by this measure mu n, which puts 1 over n mass to each of the eigenvalues. This is in general a random probability distribution, so expectation could be taken, and the expectation is called the expected empirical spectral distribution, or the ESD. Now, if the ESD converges weakly or almost surely in probability, then we say that the limiting spectral distribution, or the LSD, exists. Oftentimes, it happens that for some particular patterns of matrices, the expected ESD and the ESD converges to the same limit, which is the case for the Wigner matrix. Now, in 1955, Wigner first considered this matrix. This is nothing but a real symmetric random matrix whose entries are independent. That is in general. So the general result that goes, the most common one, is that when the entries are IID with mean 0, variance 1, then the expected spectral distribution of the Wigner matrix with scaling 1 over square root n converges weakly almost surely to the semicircle law, with whose density is given by this function fx. So now, since this breakthrough, the semicircle law had been under speculation. So people had studied it, and the limits and the moments came to be the odd moments were 0, and the even moments were given by the mth Catalan number. Like the 2mth moment was given by the mth Catalan number. Now, where the non-crossing partitions play a role is that if we consider the non-crossing partitions on 1 up to n and the non-crossing pair partition on 1 up to 2n, then their counts actually are equal, and they're equal to the nth Catalan number. So here is where the non-crossing partitions play an important role in case of the semicircle distribution, as they could be written as simply as the number of non-crossing partitions on 1 up to n, or the non-crossing pair partitions on 1 up to 2n. We remember this fact and use it later and see what happens. So now we ask a few natural questions. That is, what happens when the entries are not ID? I mean, when the entries maybe are dependent on n, or when the entries are dependent on the position of the entry on the matrix, does the LSD still exist, or the non-crossing partitions still play a crucial role in the moments? Now, in 2001, Bauer and Golinelli proved a result on the adjacency matrix of the sparse homogeneous Erdős-Rényi graph. Now, they proved the result. They are not keeping the questions that I asked in mind, but then they proved it individually, because Erdős-Rényi graph is something that was a very important topic of study. So they proved that if the the adjacency matrix of the Erdős-Rényi graph could be described as also a Wigner matrix, where the entries are IID, Bernoulli Pn, where npn is going to a fixed constant lambda, which is positive. They proved that in the expected ESD of Wn converges weakly to a symmetric probability distribution. We call it, say, mu Bg, whose odd moments are 0 and even moments are given by this formula, where this IKB are the number of some normalized 2K plates associated to certain trees that were defined by Bauer and Golinelli. Now, it could be verified that the distribution was no more semicircular. So it was important to study such matrices. Now notice that this is one matrix where the entries are IID, but the entries, like for the Wigner case, for the previous case, standard IID case we talked about, the entries were depending, the entries were IID in the sense that they were full ID matrix. The entries are not even depending on n. The distribution was not changing with n. This is one matrix where the distribution is changing with n. And just a second, just to check, am I audible?
Yes, you are.
Okay. Thank you. So the entries do depend on n. So another such model was also considered by Zakharowicz in 2006, where she considered that the matrix, the entries of the matrix were follows the distribution Gn for every n, where the moments of Gn satisfies these conditions. Now with Ck finite for all k, she proved that the ESD of Wn, where there is a scaling of scaling by root over n and the variance of Gn, converges to the probability distribution that is given, that whose moments depends only on the sequence C2k. Now the moments were described by Zakharowicz again with the help of certain trees, but this time the trees were very different from the ones that Bauer and Golinelli got in their results. So now, having considered these two, having seen these two cases where the entries depend on n, we will see another case where now the entries, now for this result we will describe later in a moment, the entries will depend on the position of the matrix. So here, what happens, we first define a graphon sequence. Now what we do is we take the unit square and we break it into grids. And on each of the grids, we define Hn to be beta ij on the ijth grid. Now, for a given graph, the homomorphism density with respect to the graphon, which is denoted by T of G comma Hn, is given by this formula. Okay. So in 2020, Zhu proved that when the entries are centered with variance of sigma ij square, this is where the variance profile comes in, where the sigma ij's are bounded, like uniformly bounded, with the condition that all the graphons with respect to all the graphons converge for every finite tree and the Lindeberg type condition, the ESD of the scaled matrix Wn with scaling 1 over root n converges weakly almost surely. And the moments are now the even moments, it converges to a symmetric probability distribution, so the odd moments are 0, and the even moments are given by this, where the sum is on the number of the trees that appear here in condition 3. Now, having seen all these results, we try to give a result that considers both these cases. Like we allow the entries to be independent. We allow the entries to be, we consider the entries to be independent and allow the distributions to depend on the position of the matrix, that is on I and j and also n. So we make these assumptions on the entries. Let Gkn be a sequence of bounded Riemann integrable functions, and there exists a sequence Tn such that n times the expectation of the truncated variables. This is given by this function G2kn, I by n, j by n. Okay, this is where we see that the entries now do depend on ij and n. And the odd moments are given by this equation. 2, the functions G2k converge uniformly to G2k, and the norms are bounded. The norms, they satisfy this Kalman type condition. Now, these conditions are, though they seem kind of mathematical and technical, they are actually very naturally true in the previous cases that we talked about, like for the standard IID case, for the Bauer and Golinelli, sparse adjacency matrix of the homogeneous case, the Zakharowicz model, and also the model that Zhu considered. So now we state our result. That is, if we consider the Wigner matrix with independent entries that satisfy the previous assumptions, and we consider the truncated matrix Zn, then the ESD of Zn converges weakly almost surely to mu prime. And with the additional condition, the truncation condition 1 over n summation ij xij square indicator of xij greater than Tn converges to 0 almost surely or irrespectively in probability, we find that the ESD of Wn also converges weakly to mu prime almost surely or respectively in probability. Now, this condition is also very natural in case of in case of the IID, full IID matrices, the band matrices, block matrices. Now there are also, okay, so there's also the law mu prime is semicircular if and only if G2k is 0 for all k, that is only G2 can be non-negative, and also the partial integral of G2 is constant. Now, as we discussed, the previous results do satisfy those assumptions, and as a result, they can be, the convergence of their ESD could be concluded from this theorem. There are other results like the heavy-tailed entries, like the band matrices, block matrices, triangular matrices, which all could be dealt with this theorem alone. Now we talked about non-crossing partitions and semicircle law. So in this case, we wanted to explore what partitions do contribute to the limiting moments. So we found that a different set of partitions indeed contribute, and we identified those partitions as these. These are the partition, we call these partitions as special symmetric partition, and they could be verified by these two conditions. If the last block is a union of even sized set of consecutive integers, and between any two successive elements of a block, the other elements from other blocks can appear, and if they appear, they will appear even number of times. Then we called that partition special symmetric partition. The set is denoted by SS2K, and all non-crossing pair partitions, non-crossing partitions with even sized blocks, they are all members of SS2K. But however, there are some crossing partitions that those are also members of SS2K. Like this partition 1, 4, 5, 8, 2, 3, 6, 7 is indeed a crossing partition, but is a member of SS2K, and hence consequently do contribute to the limiting moments of the Wigner case. So though we have found this part, now these partitions, okay, so as we see that the moments of the Bauergen, Volonelli, Zakharovich, and the zoo types, they could not be described by non-crossing partitions. However, there is a 1-1 correspondence between the trees that were between the normalized 2K plates of trees that were found in Bauer and Volonelli, Zakharovich, the trees that were considered by Zakharovich, and also SS2K. Now, the trees that were described in zoo could also be is a special case of our trees, as what we have got are colored rooted trees, and what they have considered are just simply rooted trees. So, indeed, SS2K, indeed, the moments that we get could be verified to be equal to the previous moments that were existing in the literature. So, although we have got the SS2 set of contributing partitions, there are still some questions which we couldn't answer. Like we couldn't find a closed formula for SS2K. It does not form a lattice, and also there is no recursion relation which is known for SS2K. So these are some future questions that could be asked, and I don't know, probably could be answered. And here I would like to give some simulations. Like this is for the normal standard case where the entries are Gaussian and the matrix is scaled by root n. This is the simulation for when the entries are Bernoulli 2 by n. So this when lambda in a sparse case, lambda equal to 2. Okay, this is these are some cases where we consider the variance profile. Here, indeed, we can see that the distribution of the entries are depending on n, I, and j. So, yeah, here are a few references, and that's all.
Thanks, Priyanka. So I'll have it, I mean, still a couple of minutes or so for questions. So in case anybody has any questions, please feel free to unmute yourself and ask, or post it on chat.
I had one can you just show the graph-on condition that you had? They showed.
Yeah.
The next one, the next thing. Now there are also this for graphs that have a density, edge density n to the 1 plus alpha. There are also graph-on counts for those. Do you have a CLT like this for that also? Do you know?
Sorry. Can you just repeat the question once more?
So for graph-on, for graphs that have order wedges n to the 1 plus alpha, there are also the component graph that come in. Is there a simple CLT for that also? Do you know?
No, I don't actually.
Okay. Oh, sorry, Nishant, you have a question? Okay, but can you show the last simulation for which, I mean, I was just looking at the parameter. Will these be graphons, or that if you take Bernoulli 2 by n, or the previous one, the previous slide? This is sparse.
No, here, this is sparse, yes. When
okay.
NPN, I mean, this is PN, so NPN is going to 2.
Okay. But in this, your results still hold, is it?
Yes, it does.
Okay. Okay. There was similar by, I don't know, Simon Coast and Justin Salas. I do not know. You looked, at least the graph.
Yes,
I remember Simon having a very similar graph.
Yes. Indeed, they have results, and they have shown some. They do look into the local structure also, and they show that the mass at zero or something is. They show some. They give some expression for the mass at zero.
Okay, not the empirical measure. Okay.
No.
Okay. Thanks for clarifying. Yes.
Yeah.
Okay. So now we will move to the next speaker, Anugu Sumith Reddy, and he will be speaking about Feller diffusions and so on. Sumit? Yeah, over to you.
Hi, can you see my slide?
Yes.
And the shifting also?
Yeah.
Yeah, oh, hi. Thanks for giving me the opportunity to give this talk. So I'm going to talk about a selection procedure through which we select Feller solutions out of a class of weak solutions in the degenerate diffusion. This is a work in collaboration with Professor Borkar from IIT Bombay. So what we have is a SDE with possibly degenerate noise, which would mean that there is a possibility of non-uniqueness happening in the case of weak solutions. So this question was asked in 70s by Krylov, where he actually gave a procedure through which you can actually select a Markov solution. And there isn't, but through this procedure, you may end up selecting a non-unique Markov solution, meaning there can be many Markov solutions. You are selecting one. So the procedure that we give will actually pick out a unique Feller solution. I mean, in the cases that we study, there will be a unique Feller solution, and we pick that Feller solution from our selection procedure. So the short answer is whether we can do that or not. Yes, I mean, the question we want to ask is whether we can do this or not. The short answer is yes. Under some Holder continuity on the coefficients, we can do this. So what is the process that we consider? We consider a non-degenerate version of non-degenerate perturbation of this STE, and we take a limit. If the limit exists and it has to be unique also. I forgot to mention unique. If it is unique, then we are done. So this kind of idea was actually introduced by Kolmogorov in the context of finding physically relevant solution from the class of more multiple solutions. So we just perturb it and we see where the limit takes us. So this is the perturbation that we want to look at. And since it is non-degenerate, the perturbation, we know that it is guaranteed to have a unique weak solution, and which will also be Feller. By Feller, I mean it is a Markov process and it is a Feller Markov process. So because of the duration of the talk, I will not be introducing any domains or I won't be so precise as I should be, but it will be a little more informal. So what we assume in this talk is a bounded continuity of B and sigma. And once we assume bounded continuity of B and sigma, the tightness of X epsilon can be derived easily. So, but that is not sufficient for our case, because we want to first know that the limit points are actually Feller Markov as well. And we also want to know that there is only one limit point, which means we want to know that X epsilon actually converges, or else we are not really giving a selection procedure. So that is what we want to do, and that is the most difficult part. And the method we use is to use the theory of viscosity solutions given by Lyons and Crandall in early 80s. So the notion of viscosity solution, the exact details of the definition is not really important, but all we need to know is that it is a kind of a weak notion of the solutions where you take the derivatives from the solution onto the smooth test functions. So for now, just keep that in mind. So we look at the viscosity solutions of the associated backward Kolmogorov equations with the final condition being u of x comma capital T is equal to f of x, where f of x is taken from a class of bounded continuous functions. So using this concept, Borkar and Suresh have proved that every Feller solution of of the STE, there is a corresponding viscosity solution, and the viscosity solution is just given by the conditional expectation that you can get from the Feller property of the solution. So by this, one trivial consequence of it is that if you can show that there is a unique viscosity solution, then the uniqueness of the Feller solution also follows immediately. So, and now, because we are trying to look for a limit, what we actually do is we try to see what are the candidate limit points of the perturbation. So this U superscript star and U subscript star are sort of like the candidate limit points, and what we actually show is actually, so before in defining the viscosity solutions, we first define the viscosity subsolution and viscosity super solution, and a solution is called viscosity solution if it is both sub and super viscosity solution. So one can show that the U superscript star is actually a sub-solution of the limiting equation, and U subscript star is actually a solution of super solution of the limiting equation. So, but we still don't know whether these two are equal. But in general, we can always say that U superscript star is greater than or equal to U subscript star. But proving it the other way, which means U superscript star is less than or equal to U subscript star, is the most difficult step. So in other words, we really have to show some kind of a comparison principle. So in our work, this is what we do. We show that this sort of a comparison principle holds under some kind of appropriate Holder continuity of B and sigma. So once we show this comparison principle, it is clear that these two candidate limit points are actually the same. And because they are both sub-solution and super solution, the candidate limit point happens to be the desired viscosity solution. So, and additionally, we would also get that this U epsilons are actually converging to U bar uniformly on compact sets of the respective domain. So, sorry. Now in this work, we also show that this corresponding to U bar, there is actually a Feller-Markov process. I mean, the Feller process, and we come up with the limiting semi-group corresponding to that as well. So, and now, so we can use a comparison principle and actually conclude that from this procedure, there is a unique Feller solution, because if you assume there are two different, then this comparison principle would be violated. So this will actually give us what we are actually trying to prove, which is to actually pick out a Feller solution out of a bunch of multiple weak solutions. Now I'll briefly give the sketch of the proof. So apart from proving the comparison principle, all other results like proving the tightness or proving that the corresponding U bar has its corresponding Feller-Markov process, all that, they actually are trivial once you assume comparison principle. So which would mean that proving the comparison principle is actually the bottleneck in proving this result. So, and this proving the comparison principle has been studied in the literature, but it was only for Lifshitz B and sigma. But we know from the probability literature that if you assume Lifshitz B and sigma, we know that there is a unique weak solution, which will also be Feller. So it is not really interesting, because if there is one, you will basically pick it. So we want to actually relax it to non-Lifshitz B and sigma, and a particular form of non-Lifshitz B and sigma. So what we do in our proof is we first split the domain into two parts, where both B and sigma are Lifshitz, and in another where one of them failed to be Lifshitz. Here by Lifshitz, I mean locally Lifshitz. So in the region where both are Lifshitz, this can be actually handled by classical methods that are there in the viscosity solutions literature. So that is not the hard part in the proof. So to handle the region 2, what we actually do is we fix a point in the region 2 and we construct special solutions, special super solutions around that region in such a way that that particular super solution is 0 on the region. And we use this, and we use the linearity of the problem, because you remember the associated backward Kolmogorov equation is a linear PDE. So even in this notion of solutions, the sum of two solutions and difference of two solutions, they behave in a much nicer way, as one would expect. So we prove comparison principle for these functions, u minus psi and v plus psi. And proving comparison principle for this is much more easier than proving it for u and v. It has to it has to do more with the way the proof is done. So we prove the comparison principle for u minus psi and v plus psi. And once we prove this, we just take x tending to x star, which would mean that we would actually prove that u of x star t is less than or equal to v of x star t, which would mean that u of x comma t is less than or equal to v of x comma t on the entire region. So which would actually give us the comparison principle that we were looking for. So this would prove that yes, whatever we did, taking the perturbation and taking its limit and asking for uniqueness of the limit and seeing whether the limit is actually corresponding to a Feller solution, all these things work out, and we would actually get a valid selection procedure. So yeah, thank you. Any questions?
Thanks, Sumit. So we still have a few minutes for questions. So in case there are any questions, please unmute yourself and ask or post it on chat.
If anyone is curious, this is assumptions on B and sigma that we choose.
Somehow the assumption on sigma depends on the holder assumption on V, is it?
Yes. So because when we try to construct the super solutions, the term that involves sigma is actually positive definite, or it is sign definite. Whereas the term involving beta happens to be, it can be positive or negative. So we really need to have more regularity in the term corresponding to this alpha, which is basically the term corresponding to, yeah.
But suppose B is not zero, B is not zero, let's say, that's okay. Right? Then sigma can be just holder.
B has to be greater than half.
No, beta and all. The function B. Function
sorry,
B.
B. Yeah.
Suppose B is not
B
zero. That means the ODE can move.
Yeah.
Then what happens to sigma then?
Sigma.
What's the assumption on sigma then? If B is not zero.
P can be any beta. Sorry, sigma can be any holder continuous function with exponent greater than half. Here there is still some kind of a restriction, but
okay.
Yeah, because when B is 0, we can take alpha to be like 1 or 2 or 3, anything like in that sense.
Yeah, I understand. Right. So suppose I have B not 0, then sigma just has to be a holder bigger than half. That's all.
Yes. The main reason for it to be greater than half is
both vanish. Yeah.
Yeah. So the main reason why beta has to be greater than half is because the kind of super solution we were looking for is like x minus x star to the power of gamma. But when you take two derivatives in the corresponding backward Kolmogorov equation, it would drop down by 2. So it will become gamma minus 2. To overcome that, we need some kind of we have to compensate it. So we have to take beta to be greater than half.
Okay. And also, like in the Yamada-Watanabe case, you will converge to unique solution. That is when sigma is holder half and diagonal.
Yeah. That is yes, that is true. There is already uniqueness here, so the selection procedure is like kind of like a trivial thing.
Okay, so if there are no more questions, maybe we'll move to the next speaker. Sumit, can you stop sharing? And I'll request Sayan to start sharing the screen. So next will be Sayan Mukherjee, and he will be speaking about regularized Bayesian best response learning in finite games, and he's from ISI Kolkata. Over to you, Sayan.
Am I audible?
Yes, but very low. Maybe you can increase your volume.
Hello.
Yeah.
Okay. So thanks to the organizers for giving me this opportunity. So today I will talk about regularized Bayesian based response learning in finite games, and this is joint work with my supervisor Shobik Roy, who is also from ISI. So let me directly jump into the model. So consider a heterogeneous population with unit mass, and suppose that the agents in the population have different types, which are coming from a complete separable metric space omega. And suppose that the population is distributed over these types according to a distribution design. This probability space is called as the type space of the population. Now consider a finite set S, which denotes the strategy space of the players in the population, and let delta denote the collection of all probability distributions on S. So basically delta is the n-1 dimensional simplex. Now a Bayesian strategy is a measurable map from the type space onto delta. So this means that for every type, you have a belief over the strategy space, which is given by a distribution on the strategies. So having defined a Bayesian strategy, we will now move to define what is called as a Bayesian population game. So a Bayesian population game is a function from sigma times omega into Rn, such that for every sigma, the mapping omega going to G omega sigma is measurable. So the interpretation of this definition is the following. So suppose the population the population is playing a Bayesian strategy sigma. Then agent or a player with type omega, if he or she plays strategy I, then its payoff will be Gi sigma of omega. Now a regularizer is a function from delta to R union infinity, such that it is finite on the interior, and it can be infinite but on the boundaries. It can only be infinite on the boundaries. It is smooth on the interior, and it satisfies strong convexity. It means that v of alpha x plus 1 minus alpha y is less than or equals to alpha times vx plus 1 minus alpha times vy minus gamma times alpha times 1 minus alpha by 2 norm of x minus y. So this is a stronger version of convexity, and the parameter here is gamma. So a function satisfying this condition will be said to be gamma strongly convex. Now some examples of regularizers include a well-known Shannon Gibbs entropy. So Vx is equal to minus summation xj log xj, or Sally's entropy, 1 minus gamma inverse summation xj minus xj power gamma, where gamma lies between 0 and 1, or Berg entropy. And there are several other examples as well. Now, with this definition of regularizers, we can now define the notion of a regularized Bayesian based response function. So you fix an epsilon and then define a function beta epsilon from sigma to sigma, such that for every sigma, beta epsilon sigma is basically the argmax over the perturbed expected payoff. So suppose the population is playing a Bayesian strategy sigma, then a player of type omega will try to maximize his or her expected payoff subject to some small perturbation, which is given by epsilon times vy. So this is the usual inner product, y inner product with g omega, g sigma omega. This is the expected payoff, and you perturb it using the regularizer vy, and multiply epsilon with it to make it small, and then you take the argmax. Now the fact that beta epsilon is also well defined follows, since G is measurable and V is strongly convex. Now the main target is to define a dynamic on the space of Bayesian strategies. So we require an underlying non-linear space structure. That's why we will consider the space of integrable signed Bayesian strategies to be basically the L1 functions from omega to Rn. And then with this, we can now define a Bayesian regularized Bayesian best response dynamic as follows. So fix an epsilon and consider the regularized Bayesian best response function beta epsilon, and consider the dynamic sigma dot is equal to beta epsilon sigma minus sigma. Now this actually means that instantaneously the population is moving from sigma to the best response of sigma, and in the left hand side this dot denotes derivative with respect to t. Now in such kind of dynamics we are interested in finding out existence of rest points, or in other words fixed points of the regularized Bayesian best response function. So basically we want to find a sigma star which satisfies beta epsilon sigma star is equal to sigma star, and such a sigma star will be called as a regularized Bayesian equilibrium. Now in order to prove that we require some fixed point theorems, and for that we require a weaker version of topology which is given as follows. So we will say that sigma n hat converges weakly to sigma hat if these integrals converge. Now this integral consists of an object rho hat. So rho hat is basically a measurable function from omega to Rn star being the dual space of Rn. And this inner product sigma hat rho hat of omega is defined as rho hat omega of sigma hat omega for all omega. Now a Bayesian population game G is said to be weakly continuous if for xi almost every omega in omega, the mapping sigma going to G sigma omega is continuous in the weak topology. And this then gives the existence result of the fixed point. So we consider the type space omega and xi, and suppose that G is weakly continuous. Then for every epsilon, the mapping sigma going to beta epsilon sigma admits a fixed point. So basically we show that under this weak topology, the space of Bayesian strategies is compact, and then show that under the same topology, beta epsilon is continuous. And since sigma is a convex set, by using fixed point theorems, we'll be able to show that a sigma star exists. Now, after showing existence of fixed points, we show existence of solutions, which comes from the following definition. So a Bayesian population game is said to be strongly Lipschitz if there exists a universal constant kappa such that for every xi, so xi almost every omega in omega, G, the population game G is Lipschitz. So G of sigma omega minus G rho omega is less than or equals to kappa times. So the norm of G sigma omega minus the G rho omega is less than or equals to kappa times norm of sigma minus rho. And the solution existence theorem states that if the Bayesian population game is strongly Lipschitz, then for every initial condition you are going to have a unique continuous solution sigma t, and also the fact that the semi-flow is continuous in the initial conditions, which means that if the initial conditions are close enough, then the solutions will also remain close. Now, finally, we will apply this to results in a class of games which are called as Bayesian potential games. So for that, we require a following result, which provides a sufficient condition for finding out norm compact and forward invariant subsets of the space of Bayesian strategies. So basically, you fix a compact set M inside the interior of the simplex and consider the Bayesian strategies such that sigma omega is inside M for xi almost every omega in. Now, the norm compactness and forward invariance result states that, so there are a few notations. So this gamma and epsilon, so gamma is the strongly convex parameter, epsilon is the constant which is multiplied with 3, M is this compact set inside delta, inside interior of delta. Suppose that there exists a compact set, capital Xi, inside omega such that the small xi, the measure xi is supported on this capital Xi. And suppose that for some alpha greater than 0, you consider sigma alpha m xi. So basically these are Bayesian strategies whose range is contained inside M and which is alpha Lipschitz on capital Xi. So sigma alpha m is the collection of Bayesian strategies whose range is contained inside M and which is alpha Lipschitz on capital Xi. Then the result states that sigma alpha m is relatively non-compact in sigma hat, and that if alpha is sufficiently large, meaning that it's greater than 1 by epsilon gamma, then sigma alpha m xi is also forward invariant under the RBBR dynamic, which means that if the initial condition of the dynamic is inside sigma alpha m xi, then the solution always stays inside sigma alpha m. Now we'll prove convergence results of solutions to RBBR dynamic in case of Bayesian potential games. So what is a Bayesian potential game? So Bayesian potential game is a special kind of population game where you get the payoff as a gradient of some function. So there exists a Fresher differentiable function phi from sigma hat to r such that the gradient equals the payoff function or basically the population game. And this map phi is called as a potential function of G. Now, in order to prove convergence results corresponding to potential games, we need to define a suitable Lyapunov function. So the Lyapunov function is defined in the following way. So basically, we will restrict ourselves inside sigma alpha n because they are non-compact and forward invariant. Then define phi tilde m sigma to be nothing but phi sigma minus this quantity. So it is basically adjusting the potential function, adjusting the Bayesian potential function phi by some other quantity, which is integral v sigma omega psi d. Now with this in hand, we have the following convergence result. So suppose the conditions for non-compactness and forward invariance holds, then any solution, so this phi tilde m being the Lyapunov function, it increases along every solution to the RBBR dynamic when the underlying game is a Bayesian potential game. And we can show that the omega limit sets of this solution will be basically the regularized equilibrium of the game. So this convergence will be in L1, and I think that's it. So basically, in case of Bayesian potential games, you start inside the non-compact forward invariant set. The omega limit points of the trajectories will be basically the regularized equilibrium of the game. So in particular, we are showing that in case of Bayesian potential games, the in the long run, the trajectory will be lying mostly near the equilibrium of the underlying game.
Okay, sorry, I was on mute. Thanks a lot, Cheyenne. So if there are any questions, I think we are good on time. I'll give a couple of minutes for questions. Okay, if not, thanks again. We'll move to the next speaker. So can you stop sharing, Cheyenne? And I'll request Sibsankar to start sharing his screen.
Yeah.
So our next speaker is Sibsankar Sangha, and from TFA Bangalore, and he will talk about multivariate risk measures.
So can you see my screen?
A bit louder, maybe.
Can you see my screen? Is it better?
Yeah, it's better. Yeah, thanks.
Okay.
Over to you, Sibsankar.
Okay. So hello everyone. Today I'll be talking about risk measure in terms of multivariate quantile. So this is a joint work with Marik Raj and Srikar Vadlamani. So let's start. So we'll be talking about what is risk measure and how to measure it, and the what is multivariate risk measure in terms of quantile. So what is a risk? So a risk, the word risk means hazard, chance of bad consequence, some unexpected event, loss, or exposure. So in financial context, so we say that any event that may adversely affect some institution's ability to execute a strategy or maybe to achieve its goal. So these are some aspects of risk, and so these are not all. So these are some element of the risk, and there could be some other aspects also. Okay. So now whatever the risk is, so one thing is clear that this is something which is uncertain, and that's why it should be random. And now the question is why it is important to measure risk and how to measure it. So let us see some example, and then we will try to understand why it is important. So there is some insurance company who want to sell their policy, and so they have to charge some premium to the buyers. So now how they fix the premium? So let's say they have some distribution which they get from the past experiences. So this is the distribution, and let's say so they know that something some expected thing can happen, that is the expectation of the distribution, but we know that expected things does not always happen. So there can be something unexpected thing also, that is towards the tail. So in that case, that company may face some losses. So that's why we need to introduce some risk component, that is R here. So this is the formula for premium. So that is technical premium. So, and this is a very basic toy example. So here, that's why we put here. So expectation of that loss and something is risk component, and risk component is proportional to this rho L minus expectation of L. So where rho L is the risk measure. So now, the risk measure is something which is function of the distribution. More specifically, it is some function of it depends on the tail of the distribution. But modeling the tail is very challenging, because whenever we have data, so most of the data is toward the central region. So we have very less number of data towards the tail. So that's why it is very challenging to model this thing. So now let's focus to compute the risk component given the loss distribution. Okay, so we should define what risk and what risk measure. So mathematically, we define a risk as a random variable, because earlier we have said that this is something which is random, and a risk measure is defined as a function of that random variable. So this is the risk measure, and yeah. So here this is the risk, and this we define as risk measure as some function of the random variable. And some examples of popular risk measures are variance, value at risk, expected shortfall. So variance is the deviation from the mean, square deviation from the mean, and value at risk is the number which somehow partition the whole space or real line, such that left to it there can be at least probability L, and right side there can be probability at most 1 minus alpha, and left side it is 1 minus alpha. And expected shortfall is the expected number what can happen beyond the value at risk. Okay, these are all univariate risk measure. Now we will talk about what is multivariate risk measure. So there could be more than one risky position. In that case, we had to deal with multivariate risk measure. Now, how to proceed? So many of the risk measures in univariate case are motivated from the quantiles. So let's see what is quantiles in multivariate case. So there are no unique definition of multivariate quantiles, but there are many definitions. So we pick here two multivariate quantiles. Okay, and okay. So one thing is first is geometric quantile, and another is depth-based quantile. So what is geometric quantile? So when we talk about univariate quantile, there are some index factor alpha, that is we say alpha quantile. And here in multivariate case, so we have the index factor we will use as the interior of the unit ball. The elements of the interior of the unit ball will be using as the index factor, and that quantile, geometric quantile, is given as this optimization problem. So the first component is the x minus q, that is the L2 norm, and the second component, this has no impact on the optimization problem because there is no involvement of u. So only we put here because just to make this expectation finite, and this is the usual inner product. And why this definition? Okay, in univariate case, if we instead of this inner product, if we put here 2 alpha minus 1 times q, so then this will give the alpha quantile. So motivated from that, here the geometric quantile is defined like this, and the sample version is also there. So expectation is replaced in terms of the summation. And one thing to observe here is when values of u, the modulus of u is close to 0, then this gives the central quantile. That means the values towards the median. And when the values of norm u towards 1, this will give the extreme quantile. Now let us see the contours. So these are the isoquantile curves. So here the first one, this blue one, so that is corresponding to the value of norm u equals 0.2, and we take the modulus same but in different direction, and we plot this thing. So they somehow we can see here the different level of contours. So they somehow order the data towards the from outwards from the median. Okay, and now let's explore some properties of this quantile, whether they are good or not. So this geometric quantile can uniquely characterize the distribution. That is, if we are given some quantile function, so we can uniquely characterize that what is the distribution. That is to say, if there are two different distributions, their quantile functions should be different. So they uniquely characterize. And okay, another thing is, so quantile should so from univariate context, if we see, quantile should order the data set. But here we see that geometric quantile can go beyond the convex hull of the data, even if the distribution is compactly supported. In that case also, quantile can go beyond the data. So there is no meaning of this thing. We don't know how to explain that. And this is some negative part of this quantile. Okay, now let us see how this quantile decay towards extreme. That means when the value of norm mu is going towards 1, how they behave with different type of distribution. That means how they behave with the heavy tail and how they behave with light tail, and if we assume some sort of moment condition, and how they behave. So here we have results. So one thing to note here is, so quantile, when you are given some index vector u, that is whose norm is less than 1, then quantile, so norm qu, so its direction is not the same with its direction is not same with the u. So if we write it here, unit vector, so that is not same with the u, the direction are not same. So here, but when u is going towards 1, norm u is going towards 1, so then they converge. So now how at what rate they are converging? So we normalize with this constant, and in colored thing. So this result was proved by Girard. So this colored thing is going to 0. This result was proved by Girard and Stupler in 2017. So they proved that this quantity, if we normalize by norm q g alpha u, that is going to u. But their result, so there is a some disadvantage. So they converge to this quantity, but you can see this is only some distributional quantity, or more specifically, they give some sort of central property. That is, if to distribution, okay, there could be some different distribution which has this same quantity of this same expectation of this quantity, but their tail behavior could be very different. So in that case, this quantile cannot distinguish these two distribution. So here we go one step more further. So we subtract these two things and normalize with this quantity, that is norm of the quantile, and then we get this thing. And we also assume one more moment condition, that is second moment. In their result, it was they assume the first moment. So in that case, here also we get some quantity which is distributional quantity. So there could be some distribution which is this quantity same but different tail behavior. So here we note that this result can be further extended. I mean, one can get more strict rate of convergence using the same technique. And okay, and another result, this is about the norm of the quantile, how the norm is going to infinity. So in their result, Girard or Stupler, so they proved that this quantity is going to the trace of sigma. Sigma is covariance matrix here. So the again the same thing, that there could be two different distribution whose tail behavior is very different, but their covariance matrix may be same. So in this case, this quantile cannot distinguish them two. So we normalize with this quantity and we get the this result. Okay. Now we'll be talking about another type of quantile, that is depth-based quantile. So before that, let's understand what is depth. So depth is a non-negative function corresponding to a distribution which gives some sort of ordering of the data, or which determines how deep a data point is corresponding to the data set, or in terms of distribution, how deep a point is with respect to that distribution. Okay, there is no unique definition of depth function. So in 2000, Circling gives this definition that a depth function should satisfy these things. Okay, sorry. Yeah. So now a highest depth point is called a median, and points outside the convexal of the data set, then the depth will be, if we define a depth, then the depth will be 0. So these are some desired properties of the depth function. And now let us talk about some particular depth function, that is 2K depth. So that is introduced by 2K in 1975. So that depth function is, so this is the definition is like this. And so let us understand, try to understand through this data set. So if you have data set, so now the depth corresponding to this point will be, so you take all the hyperplanes passing through this point and you take only that hyperplane which gives you the minimum probability. So here the definition is infimum of probability of X such that that contains the X. So here we take 10 data points, and if we want to compute the depth of this point, so we can see that only this hyperplane, if we take this hyperplane, this side there is only one data point. So there could be several other half space also. So for this case also there is only one point containing this half space. But if we take some other things, let's say we take this hyperplane, then you can see this side or this side there is this side or this side there are more than one data point. So we'll take the minimum. So that's why the depth of this point corresponding to this point is 1/10. Okay. Now similarly here we draw the depth contour. So they also order the data, and they like geometric quantile, they don't go beyond the convex hull of the dataset or support of the dataset. They remains on the dataset inside the dataset. So that is a advantage of this thing. And now similarly, let us see how this quantile behave with the extremes. That means towards the tail, how this quantile behaves. So here we have two results. So X is a RD valued random vector, and lambda is some positive function, and Vt is regularly varying function. So regularly varying means roughly we can say that it is polynomially decaying, and we assume that the distribution has density, and density also decay polynomially. So this condition gives you that it decay polynomially, and this condition gives you that the decay is uniform. That is, it is uniformly decaying. In that case, we can prove that our half space depth that is also decaying polynomially. And the right hand side quantity, that integral is finite, that we can prove from this thing. It will follow from there. So so when we assume that some distribution is regularly varying, that means it is polynomially decaying, and we are getting that our half space depth is also polynomially decaying. So in some sense, this quantile is doing good here. And for light tail, so what do we mean by light tail? So let X be some random variable, and capital F is the cumulative distribution function, and their marginals are F1, Fn, and we give some dependent structure C here, that is some popular. And if we have this result, so that is general result, but this result can be used to analyze the light tail thing. So half space depth is bounded by the survival function of one of the or any of the marginals. So that is somehow, let's say if you have some light tail distribution, so any one F1 or Fi or Fn, so in that case your half space depth will decay exponentially fast. So here we give some outline of the proof here. So let's say this is this side X1 is, let's say, heavy tail, and X2 is light tail. So in that case, if you have to compute the depth of this point X1 and X2, sorry. So if I have to compute depth of X1 and X2, so we can take several other any hyperplanes, but if we take this hyperplane, then we can say that this side the probability will be only of the light tail probability. So it will decay exponentially fast. Okay, that's what I want to tell. Thank you for your attention.
Okay, thanks, Sibsankar. So any questions? please feel free to unmute and ask or post it on chat. Okay. So if not, let me start.